So why do solids that look so similar behave so differently? So for example, we have here some salt and some sugar, and they look pretty much the same. However, there are lots of different properties that are different between them. So, first question, why do they dissolve differently? Well, sodium chloride is made from a positive ion and a negative ion, and they form together, what do they form? They form a, what's this structure? Crystal lattice. Okay, so they make a salt crystal, a crystal lattice. And if we look at water, because we're going to have an interaction between the salt and the water, and just as we're starting this, we're going to remind ourselves that the most electronegative elements are FONCH. Okay, so fluorine is bigger than oxygen, is bigger than nitrogen. The most electronegative are these three, the FON, and then the CH just kind of goes at the end because it lets us know that they are less electronegative. So there's FON or FON. Those are your most electronegative. And then the other ones, we're just putting them there so you know that they are less than nitrogen, but they're approximately equal to each other. Carbon and hydrogen have very similar electronegativities. Yes? Okay. Now, bearing this in mind, we have water, which is made up of 2 hydrogens and an oxygen. And if we were to draw the dipole for each bond, if I drew an arrow along that bond on the left, which end would the arrowhead go on? Would it point towards the H or towards the O? It would point towards the O. And what goes on the other end of that arrow?
A line.
A line. And why do we have that little cross thing at the end of the arrow? What does that represent?
Positive.
A positive charge. Okay, so we have our 2 bond dipoles. What do we get as our net dipole, the overall dipole? Which direction would that point? Have a chat with your neighbor about that.
Are we finding the net dipole?
We're finding the net dipole. And what you're going to do is you're going to point in the direction that you think that net dipole points. Yes, it points up. Now, why does it point up? Because both of the bond dipoles point up, yes? But one goes left and one goes right. So the left and right cancel out, yes? But the ups don't cancel with anything, yeah? So the net dipole is whatever cancels out is canceled out, and then whatever you're left with is the net. And so we then have an up dipole. with the positive end at the hydrogens and the negative end at the oxygen. And because we have a dipole, what kind of molecule is this? Is it a polar molecule or a non-polar molecule?
Polar.
This is a polar molecule. And remember, these are called dipoles because what does di mean? Two. And what does pole mean? End, essentially. So this molecule has two ends. It has two different ends. Okay, it has two ends, two di ends, poles, and we have two different ends. One positive and one negative. And it is because water is polar that it can dissolve sodium chloride. In order for sodium chloride to dissolve, what do the sodium and chloride have to do? They have to dissociate. Now, positive, negative, they're attracted, yes? Why would they bother? Right? It's kind of like, what would you have to do? Would you get energy out or would you have to put energy in order to break that ionic bond? You would have to put energy in to break that. And nature doesn't like putting energy in, yes? However, we know that salt does dissolve, so there has to be something else at play there as well, yes? And what's happening is that although we are breaking ionic bonds, what you can see here is that we are forming intermolecular forces between the negative ion and the positive hydrogen. And if you look at all of the negative ions, they are all surrounded by the white hydrogens. Yes? And then if we look at our positive ions, the little purple ones, I really wish I could give you a color book. That would be so much better. But anyway, you've got the little positives there, and they are all surrounded by the negative oxygen. All the little red oxygens point towards the positive ions. So we are forming those intermolecular forces. And when intermolecular forces form, is that an endothermic or an exothermic process? That's endothermic. Exothermic. Because they want to be closer to each other. They automatically fall there, which means they're then releasing energy. Okay? And we'll get a better picture of this over here. Okay, so we can see up close, we have sodium in the middle, and all of the slightly negative oxygens are pointed towards the sodium. This particular structure, where the sodium is surrounded by water molecules, that structure is called a hydration sphere. When the ions get surrounded by water molecules, that process is called hydration. Why is it a hydration sphere and not a hydration circle? Yes?
They're 3D.
Because these things are all actually 3D, okay? So it's not a circle. So actually 3D. Therefore, it is a sphere. So you get a hydration sphere around sodium. That's just the little water molecules that surround sodium. And you get a hydration sphere around chloride. And you get the positive hydrogens are all going to point towards the chloride. You should be able to draw this kind of diagram for your Unit 8 test, which is not tomorrow. That's 6 and 7. But when we come to this one, be able to draw for the Unit 8 test. Okay. Now, the intermolecular force that is happening between here, you know what's really nice? We have, if I get rid of that one, we have over here a dipole. And it is attracted to an ion. Yes, and there is an intermolecular force between them. Imagine what we could call that intermolecular force. Wouldn't it be logical if we called it an ion-dipole force? Wouldn't that be nice? And guess what? It's called an ion-dipole force. Every once in a while, the chemistry gods shine upon us and we get a logical name. Yes, isn't that nice? It's an intermolecular force between an ion and a dipole. Like that one, yeah? Okay. And if you want to turn, make sure you have your little data page out where we are over here. Okay, we're going to take a look at our ion-dipole force. These are non-bonding intermolecular forces. So down on the bottom half of the page are your IMFs. And the very tippy top of the IMFs is the ion-dipole. That means it is the strongest of the intermolecular forces. And these numbers over here show that it takes between 40 to 600 kilojoules per mole to break those IMFs. Yeah? And then, of course, if they form, that's the amount of energy that is released when they form. Yes? So either it's the energy required to break them or it's the energy released when they form. Let's go compare that to the ion-ion force, the ionic bond. Okay, so up at the top of the page, we have not IMFs, but we have actual bonds. Okay, so at the top of the page, we have our 3 types of bonds, ionic, covalent, and metallic. And if we look at ionic bonding, we have between 400 and 4,000 kilojoules is how much energy is required to break the bonds or released when they form. So you remember when we said ions don't want to break apart, that's going to require energy to put in. Putting in energy is not spontaneous. If I want this pen to come up off the desk, I have to put in energy. That does not happen on its own. It does not happen spontaneously. Falling down, that's spontaneous. That's a release of energy. You can even hear the energy come out. Yeah, some of it came out as sound energy. Some of it's coming out as heat energy, right, in the table because the particles are moving more. Yeah, same thing. When we have particles come together, that's going to release energy. If we break them apart, that's going to require an input of energy. So nature doesn't want sodium and chloride to split apart. However, nature is perfectly happy for an ion to get together with a dipole, releasing energy. So now we have both an input of energy and a output of energy. Yeah? So we can actually get this whole thing to be overall a favorable process. Yeah? And it's not, there's a little more to the story than that. Nature also likes things to become more random. And what's more random? A salt crystal or individual ions floating all around? Ions floating all around. You don't have to worry about that for this year, that randomness piece, but that is also something that pushes reactions forward. Is if things are becoming more random, nature says, good, thumbs up, let's do that. Okay? So we're getting IMFs forming. That is thermodynamically favorable. It means, yes, we like that exothermic process. Yeah? Okay. So that is our ion dipole force. Back to here. Okay, so we have our polar molecule. You can get these ion dipole forces when the molecule is polar. All right. Now, here is a picture of sugar. And this is going to explain how sugar dissolves differently and gives you a solution, say, that does not conduct electricity. We're going to look at that more closely. Here is a structural formula of sucrose. And every one of the corners every corner is a carbon. Okay, so we got a carbon there, 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 and we got one there, 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 there. And if you were to count up all of your carbons in this structure, you would end up with C12 and all your hydrogens, H22, O11. Okay? And the ending ose that tells you that you have a sugar. Yeah. And we got into a little discussion in my other block about carbohydrates and sugars and starch. Are we interested in that, or do we just want to move on? You're interested in that. Okay, cool. It won't take very long. It'll just take a moment. Okay. Sugars have that ose ending, and if you look at their structure, what elements do they contain? Carbon, hydrogen, and oxygen. And these are carbohydrates. And if you string a lot of sugars together, simple sugars, long sugar chains are also carbohydrates. Sugars are carbohydrates, and these long sugar chains can include starch. Okay, and that's how, like with, if you eat bread or pasta or something like that, you're eating the starch, and so your body breaks those down into simple sugars, and then your body uses the glucose that is released, which is a simple sugar, and it burns it for fuel. Okay. We have starch, we have cellulose, which is like in trees and grass. We can't digest it, but cows can. Okay. In fact, the cows can't, but the bacteria in the stomach of the cow can, so the cow can. It's got a helping hand, though. And we have polysaccharides. Polysaccharides. You are not responsible for any of this, but, it's kind of interesting, and if you're planning on taking Biology 12, it will be helpful. Now, if we go over to our ball and stick model over here, you'll notice that we have hydroxyl groups. We've got this OH group here. Yes? Okay, so we've got OHs all over the place in this structure. And what do you remember about O compared to H? O is much more electronegative than H. So what that means is that that bond is going to be polar. So you have a positive and a negative, and you have a positive and a negative and a positive and a negative. You can see they're all over the place. So you end up with these little positive areas all around the outside of the sugar and these little negative areas all around the outside of the sugar. We also have some plain old O's in there that can interact. Woo, what just happened there? Okay. And if we go over, we can see in our space filling model, you can see around the outside, we do have those positives and negatives. And if you were to take two of those, they would slot in beside each other. We might have maybe these two negatives on one molecule interacting with these two positives on another molecule, and they come together kind of like that. They just kind of like and stick. The positives stick to the negatives. And what do we call this kind of interaction? Well, we've got dipoles interacting with dipoles. Guess what that's called?
Dipole-dipole?
That's a dipole-dipole force. Okay? And I think that actually says that on the next page, so let's just go check. Oh yeah, look, a dipole-dipole force. So for example, if we look at, and this is when we put it with water, the water has a dipole, and this area of the sugar has a dipole. And so then that's why we have a dipole-dipole force, the positive and negative interacting. Love these names, right? You got an ion with a dipole, ion-dipole. You got a dipole with a dipole, dipole-dipole. It's good, right? And the sugar bonding to the sugar is also dipole-dipole. All right? But because hydrogen is bonded to oxygen, it's a little bit different. There's a special type of dipole-dipole when hydrogen is bonded to either oxygen, or who do you think the other two are? Oxygen. What's special about oxygen? Oxygen is very electronegative. Who are the other two who are also very electronegative? Nitrogen and fluorine. So if hydrogen is bonded to one of those three, we can get a special type of dipole-dipole interaction. And that is called a hydrogen bond, an H bond. Okay? So in a hydrogen bond, what we have to have is we have to have an N, an O, or an F bonded to an H. Okay? We also have to have another N, O, or F, and it doesn't matter what it's bonded to. It can be bonded to an H, it can be bonded to something. But this is on one molecule and this is on a different molecule. So in between those two molecules, we get the intermolecular force called hydrogen bonding. That is a sad name. I don't like that name because is hydrogen bonding a bond? No, it is a intermolecular force. And AP will be unhappy with you if you call an IMF a bond. Okay, so make sure if you're talking about IMFs, you talk about IMFs, and they will be okay with you using the abbreviation IMF. It is a standard abbreviation for intermolecular force. Okay. Now, the reason that we have that these are able to be so positive, actually, before we do that, let's just talk about electrostatic attraction. What are the, and I'm doing this because I want to use my hands later and you'll be able to see them a little bit later. What are the two things that affect electrostatic attraction? Coulombic attraction. Coulombic attraction, the attraction between positive and negative will be bigger if what? Have a chat with your neighbor. What makes positive and negative stick together more tightly? What makes that force bigger? Anyone got one of those things? Yes. Distance. So the further away they are, is the force going to be bigger or smaller? Smaller. Okay, so the distance is one thing. What's the other thing that makes a difference?
Atomic radius.
Atomic radius, that has to do with distance. Okay, so that's just another way of saying distance because you're looking at the distance between charges. Yes. Electronegativity, yes, but there's something about the atom that gives it its electronegativity. Yeah? Sorry? Zeph? Yes. More specific, more general, actually not more specific, more general than Zeph, we can just say charge. Yes? Is that what you were thinking? Is that what you were thinking, Edward? Why did you not say something? Anyway. So the amount of charge. So if we have a greater positive charge, it's going to be more attracted. If we have a greater negative charge, it's going to be more attracted. So the greater the charge, the bigger the force. Yes? So when we have hydrogen, we're going to get into both of those things. First of all, if my elbow is oxygen, yes, and my fist is hydrogen, hydrogen only has one proton and one electron, yes? So if oxygen pulls all that bonding electron density over here, how many electrons are left around the proton? Basically nothing, yes? We basically have I like to call it a naked proton. Yes? Now, how big are protons compared with the size of an atom? Not big. They're really, really tiny, okay? There's actually an analogy, and I think it's in my grade 9 book, that says if you have an orange and you put it on like a baseball field on the pitcher's mound, and then you drive 10 kilometers away, that would be the atomic radius. So basically, orange is like the nucleus that contains the protons and the neutrons, and the size of the atom is like 20-kilometer diameter. I have trouble even imagining, like, in my head how far that is. That's really far. Yes, it's not like the baseball diamond. It's not like the stadium. It's like 20 kilometers in either direction. That's the edge of the atom. So if you can get rid of that electron cloud, all of a sudden you have a very, very, very tiny particle. And that means that other things can get very, 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 very close. And if things get very, very close, what happens to the force? It gets very, very strong. Okay? So that's why it's hydrogen bonding. That's why it has to be hydrogen, because hydrogen has no core electrons. So when you take that valence electron and pull it away, naked proton. Anybody else? They all have core electrons, right? The only one that doesn't have core electrons is helium, and helium does not bond. Yes? That's why hydrogen is special. And it has to be partnered up with either oxygen or nitrogen or fluorine, because they're the only ones powerful enough to pull the electrons away far enough that you get that little naked proton. Yes? So that's why we need to have nitrogen, oxygen, fluorine, and we need to have hydrogen, because we can essentially remove its electron density almost entirely. Yeah? And that is why when we compare hydrogen bonding the kilojoules per mole here are larger than just any old other dipole-dipole interaction. Is good? Okay. Now, just while we're here, someone in the other class asked me if you could have, say, an oxygen, attached to a hydrogen, and would it be okay if the other molecule was like a nitrogen and we had its lone pair there? That's fine. Yes? I don't know why I have a lone pair there. It should be a bond. Yeah, so it doesn't have to be the same thing. It can be either. Do you know what I mean? You could have a nitrogen or an oxygen in either place, or a fluorine for that matter. Is good? Okay. So now we just talk about this special type of dipole-dipole bond. This is back on page 41. Our special type of dipole-dipole bond, which is the hydrogen bond, and it occurs between the hydrogen that is bonded to oxygen or NRF and the lone pair on a different NRF, ONRF, called hydrogen bonding, or H bonding for short. Okay, are we good? All right, just bear in mind, this covalent bond, that's not your hydrogen bond. It's that intermolecular force in between. Now, I remember in the other class, I actually did something a little earlier. No, let's finish hydrogen bonding first. So here's hydrogen bonding. We've got hydrogen bonding in ice and hydrogen bonding in liquid water. And I'd like you to notice that the structure that the ice takes, what kind of shape do we get with our molecules? What shape do they form? They form a hexagon. Have you guys ever seen a snowflake up close?
Yeah.
What shape are they? Hexagons. They either are hexagonal or they have 6 points, and that's because this is the most energetically stable. This is like the most stable arrangement of water molecules when they are not moving. Yeah? You'll notice with liquid water, the molecules, H2O molecules, are closer. And in water, those hydrogen bonds are constantly breaking and reforming. So in ice, the hydrogen bonds are stable. In the liquid, they're breaking, they're forming. The water molecules are like, I'm going to move over here. And then they form a new one. And then they break away from this one. And they're like, I'm going to move over here. And they form a new one. Is good? Okay. What property of water is kind of weird that is explained by the fact that we have this hexagon with lots of empty space in it, and that the water molecules are more tightly packed in liquid water? What's kind of strange about water? Solid water versus liquid water. Usually solids would be more tightly packed. A little bit, maybe, okay? Not necessarily a lot, but a little bit. So normally solids are more dense than the liquid form. However, in water, liquid water is more dense, and solid water is less dense. Then when we get into gaseous water, the particles are, number one, they're too far away from each other. Big distance. They're too far. And they're moving too fast. For those intermolecular forces to be important. Yes? If you happened to have gaseous water and one particle was just by random nature just moving a little slower, right? And another one was moving slower, and if they got really close, what would happen? They would condense. Yeah? So the more you lower the temperature, the more likely that is to happen, the more likely you are to get condensation. Yes? That's one of the reasons why the air dries out so much in the winter, because, right, it's colder, and so you get more condensation, so there's less actual water vapor in the air. All right. Let's take a look at this molecule here, and you're going to tell me if this yellow hydrogen can be involved in hydrogen bonding. Can it hydrogen bond? Yes or no? I got one nod from someone. I got another nod.
Yeah.
Yes? Why can it hydrogen bond? Yes?
Because it's already bonded to an oxygen, and if there's another X,
Yeah, because it's bonded to that oxygen, it is allowed to hydrogen bond. And why does it matter that it's oxygen, nitrogen, or fluorine? Because those three are strongest electronegativity, so they will rip that electron density away from the hydrogen. How about our green hydrogen? Can it hydrogen bond? Tell your partner why or why not. Can it hydrogen bond? Thumbs up, thumbs down. Thumbs down. Why? Because it's bonded to carbon. And what do we know about carbon and hydrogen? Their electronegativities are similar. Yeah? Okay. What do we call this group here? The OH group. That's called a what group? Hydroxyl group. And the hydroxyl group is also found in what category of organic chemicals? Yes.
Carbohydrates.
They are found in carbohydrates. What other one? Yes. Alcohols. Okay, so alcohols also contain hydroxide groups. Not hydroxide, hydroxyl groups. Okay, good stuff. Excellent. And just before we move on, I wanted to talk to you about what I talked to the other class about, and I'm just going to add an extra page here. You can do this anywhere, or you don't even have to write it down. We're going to come across this later. The question we came across was, why is NaCl more soluble than CaO? Actually, let's make it even more obvious. Let's make it MgO. Feel free to take a look at your periodic table. Okay. We have sodium, chloride, we have magnesium, oxide. What has to happen in order for NaCl or MgO to dissolve? You told me earlier. Yeah? The ion-dipole thing has to take place, but even more simplistic than that, just what has to happen to the sodium and chloride ions? They have to dissociate. Yes? So, these guys are going to dissociate, and same thing is going to happen for MgO. Why might it be more difficult for MgO to dissociate than NaCl? Yes, Emma? Yes, these guys have a bigger charge. Therefore, we have a stronger attraction, coulombic attraction. Therefore, it's a stronger ionic bond. Any other reasons? It doesn't help that I've done a terrible job at drawing my circles, but yes? The oxygen is smaller, yeah, than the chlorine. So what does that mean about the distance between the positive charge and the negative charge? The magnesium can get closer to the oxygen's positive nucleus than sodium can get close to the chloride's positive nucleus. What happened to my pen? Oh, there we go. Okay, so sodium chloride, you throw it into water, it dissolves. You throw calcium oxide or magnesium oxide into water, it sits there. Does nothing. I lie a little bit. There's a chemical reaction that takes place, but it doesn't dissolve nicely. Okay, and that's it for that. Do we want a 5-minute break? Okay, let's have a 5-minute break and we'll come back and we'll talk about the force that doesn't have a good name, London Dispersion Forces. That's not a happy name. Yeah. Okay, so 5 minutes, 1:45? I think 1:45 will do us. Okay, we are now on page 43, 43. So make sure your phones are away. Here we have an iodine molecule, I2. Iodine is atomic number 53. So each atom has 53 protons and it has 53 electrons. Yes? That means in total, iodine has 106 electrons. Lots of electrons. I've only drawn a few of them here. Yes? And you can see, actually, if you look up close on here, you can see how I had to cut and paste them. I don't know if you can see these little tiny like white lines here and here and here and here. I cut and pasted all those. So that was kind of fun. But anyway, this is our iodine molecule. And every once in a while, because these electrons are just moving randomly, they could end up mostly on one side. Okay? By random chance, by random motion, all the electrons end up on one side. Or most of them anyway. And guess what that creates? That creates a dipole. But this is not a permanent dipole. It doesn't stay there forever. So we call it a temporary dipole. But in the world where there is one I2 molecule, there will be another I2 molecule. And let's say that it's the neighbor. Okay, so we have two neighboring I2 molecules. These guys are neighbors. Now this guy over here has a temporary dipole. Now its neighbor, it's got its own set of electrons, which are in motion, and they see this slightly negative end. And what do the electrons in the second iodine molecule do? They get repelled, okay? And they flee. They run away. And so what do we end up with? We end up with our original temporary dipole, and we end up with a second temporary dipole. This one, the one that happened by random chance, that is called our temporary dipole. And the other one, it was caused by the first one. So if something causes something else, we can say it induces it. Okay? Have you ever heard of somebody inducing labor? Like for a woman who's pregnant? You've not heard of that? Oh, so if a woman is pregnant and they need to say she's overdue. It's supposed to be like 39 weeks or say something. Say she's at 42 weeks. And they're like, dear God, let's just get this baby out of here. It's getting too big. It's going to have a hard time fitting out. They will induce labor. So what they do is they actually put a hormone called pitocin. They give that to the mother, and it is the thing that starts contractions. Okay? So they are causing labor to happen without it happening naturally. Yes? So it is causing it to happen. That is what is induction is when it is caused to happen. So this temporary dipole induces the other molecule to also have a dipole. So we call this second dipole an induced dipole. If something is induced, it is caused to happen. So the temporary dipole induces the induced dipole. You're good?
And what caused it to happen?
What caused the induced dipole to happen? The temporary dipole. The temporary dipole said, look at all my beautiful electrons. Yes? And then this said, I'm repelled. And so all these electrons then flee to the other side because of this temporary dipole. So the temporary dipole is inducing the movement of the charge to the other side.
Because of the slightly positive?
Yeah, because this end is slightly negative. The electrons move away from it, which leaves this end being slightly positive. Yeah. Yes, they do, and they can, which is why these are not going to be like super strong forces. If it was there all the time, it would be a much stronger force. Yeah, it can just randomly go back. Yes? Now, you do tend to get a bit of a domino effect with this, because you can see, oh, if I've got this temporary dipole and this induced dipole, then what might happen to the neighbor that's one over? You could also get an induced dipole. But of course, there's movement, and the electrons are moving, and the molecules are jiggling, and all this kind of stuff. So eventually everything's going to go back and just not be a dipole anymore, which is why these forces are usually one of the weakest kinds of forces. However, the strength of these forces depends on the number of electrons present. Yes? Because if we've got iodine, we have 106 electrons. Yes? But if we have fluorine, F2 has only 18 electrons, right? Because each fluorine has 9. So you can imagine if all of those 9 electrons went to one side, it's not going to be anywhere close to, even if I got like 3/4 of these over here, that would be a bigger negative charge, and it would leave behind a bigger positive charge because the nucleus also contains more protons. Yes? Okay. This actually goes to explain, do you remember how we had to learn in the reactions unit that iodine is a solid and bromine is a liquid and chlorine is a gas and fluorine is a gas? Well, if you say to yourself, iodine has tons of electrons, therefore it can form a fairly large temporary dipole. So the intermolecular forces will be quite large. And therefore, when the forces are quite large, the molecules tend to lock into place and they will be a solid. Bromine has only 35 times 2 is 70. It has 70 electrons. So it's still not bad, right? So you will get a temporary dipole. It won't be as strong of a positive and negative charge as this. And so you do get those interactive forces, the intermolecular forces. They're still strong enough to hold it together, but they are weak enough that they break and reform and break and reform. And if the intermolecular forces are breaking and reforming, what state of matter do we have? We have a liquid. Yes, so that's bromine. Then we move to chlorine, which has only 34 electrons. How big are its partial negative and partial positive charges going to be? Not very. And that's why chlorine, when a chlorine molecule passes by another chlorine molecule, it's unlikely that they're going to have enough force to cause them to come together and condense. Yeah? Okay. So, what do we call these lovely forces between temporary dipoles and induced dipoles when we have originally a non-polar molecule? Sadly, they're not called temporary dipole induced dipole forces. That would be lovely if they were, but they are not. They are called London dispersion forces. Now, the good news is that these are very, very commonly referred to as LDFs. They are also known as London forces, they are also known as dispersion forces. And that one, there's no really great way to remember it. I mean, it's to do with random movement. It's kind of like when you have dispersion of a substance in water. When it dissolves, you get random movement, and that's why it dissolves. In this one, you get random movement of the electrons, and that's why they can end up all on one side. That's kind of where it comes from, but I don't know that it's very helpful because in one it seems to be getting more organized and one it seems to be getting less organized, so I don't know. Yeah.
Where did the London come
I don't know. Maybe the guy who discovered it, and I say guy because everything happened back in the early 1900s, right? And there was all men back then doing the chemistry except for Marie Curie and her daughter, right? I'm sure there were others, but they didn't get much credit even if they did stuff. Yeah, so that's why, probably named after somebody, I would imagine. And that's where I got to with my other block. And we said, hey, we're done for the day.
from?
Yeah?
Right.
Yes.
How long is the question mark?
How long is the test tomorrow? There are, is it 21, 24 multiple choice, 21, 24, somewhere in there. And then there's 5 written, 6 written, something like that. I don't know. It's 6, like it's 3 pages front and back. But I left like tons of room for each written response questions because I have a few large writers and I want to make sure that they can fit it in without, having to cram it because it gets really ugly, right? And it's nice to be able to just have it tidy. And AP lets you use as much space as you want, basically. They just give you a book and you write in it and off you go. Like there's no, yeah. You guys get to do your multiple choice on the computer. That's going to be new.
Spend 10 minutes charging my phone.
Yes, go for it. Feel free to move things out of the way too if they're in the way there.